All right, let's see. Okay, we'll get started. Last day of, sorry, not last day, last week of classes. Feels weird. It's been a long semester, I guess, or maybe a short one. So yeah, I was hoping to cover some stuff. I mean, okay, so we're going to be covering neural networks. I don't have slides for this, so it'll all be on the iPad. Maybe I will need to extend the deadline again because I actually don't think I'll have time to talk about calculating gradients, which is sort of what you need to do for the assignment. So we're going to start with sort of basic introduction to neural networks and then see where we go from there today. Yeah. But I mean, in any case, it's good to look at the homework, sort of have a feel for like what you don't understand and so on and so forth. Okay, what else? Yeah, okay, let's just get started. I know it's, well, first of all, usually we actually end up covering a lot more, but for some reason this semester we haven't really been able to cover so much. So it feels weird, I guess, to sort of just talk about neural networks and not actually sort of, work further and like go into like more fancy neural networks, even though we have, like recurrent neural networks is an example of a neural network. So whatever, let's just talk about neural networks. Okay, so intro to neural networks. Yeah, so this is sort of I wouldn't say history. This is just trying to give you some intuition and background about like, why we call them neural networks, how they came to be, and where we are now with neural networks. Right, so the name of them, neural networks, suggests that this should be something related to the brain, and that's really ostensibly the goal, right? So the goal really for neural networks is to somehow emulate our brains, right? Through some type of computation, and in particular, what we're going to look at is like emulating sort of how these neurons work in our brain. So, I'm not going to get into too much detail about the biology of it, right? So, the neurons, they look a bit like this. I've forgotten what these names are. Anyone who's a biologist can tell me. I remember there's something about axons or something. So they look something like this. And the key point is that they have some input. And if you have enough input, then these neurons fire, right? So fire basically is like some output, right? So either they don't fire or they fire. And so one way you can think about modeling them is, is taking some data and depending on how much, depending on the magnitude of the data it sees, it's going to output a 1 or a 0, depending. Right. So what people try to do is, okay, let's come up with just a very standard, simple model for how this would work, right? So this was in 1943. So this is McCulloch and Pitts, 1943. And so this is sort of a, very simple way of modeling this, right? So we could have inputs, xn, and then you could take a sum, and then that's going to get you into some like threshold function, right? It gives you an output, either 0 or 1, right? So essentially what I'm saying here is that, in math, it's basically y equals to, let's say, the indicator function that the sum of I from 1 to n, xi is greater than some t. Right, so t being some threshold here. Right, so this is one very simplified model for how you would model a neuron. So you have some inputs, x1 to xn. You take a sum of them, and then you check if your sum is greater than some threshold, and if it's greater than some threshold, the neuron fires and you can pass through, right? Okay, so what's sort of wrong with this model, or anyone have any comments about this model so far? Seems very straightforward. No comments? This is a perfect representation of the brain. So let's see. So one thing about this is that this model in some sense is fixed, right? Well, okay. So there's one parameter here, which is t, right? So there's one parameter here, which is t, and so that's sort of, you could basically play around with that. But in terms of the inputs, there's nothing really you can do about it. You're just taking a summation, and then you have some threshold, right? And so this is not basic, so this is not that great of a model, in part because you're not really trying to model the fact that we learn. Is not incorporating some notion of learning, right? Right, exactly. So Tony says maybe some xi's matter more than others. And so, yeah, so this is a fairly simple thing you could piece of intuition, which was sort of realized by Hebb. And basically what he said, I mean, he wrote this in terms of like neurons, but what he said was essentially repeated firings strengthen connections. Right, and you must have heard of this before, the idea that like, how do we learn? We learn basically because, these particular neurons fire, and if they fire in some certain configuration, then that's going to strengthen that configuration so that next time it's easier for that particular thing to fire. Yes, oh, yes. Neurons that fire together, wire together. That is a much more succinct way of saying that. Nice. And so the key point here is that, this is, in some sense, the essence of learning. I mean, okay, we're not going to get into, the actual neurochemistry or sort of psychology of what learning means, but, you can think of this as some form of learning, right? And so again, this is pretty, obvious. What we can do is basically just add weights, right? If you add weights to something, now all of a sudden, if those weights change, then that is tantamount to saying, okay, I care about this input more than before, right? So what we're going to do is let's just, well, okay, let me just okay, let me copy and paste this. Okay, now I'm just going to add it here, right? So what I now have is I'll have W2, blah, 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 WN, right? So in particular, okay, well, sorry. So this is basically Rosenblatt. This is called the perceptron. I guess maybe some of you have heard this. This is sort of the first neural network model. And basically what all he does is basically replace the ones now with weights, right? So what you have now is you have indicator sum of xi wi I from 1 to n greater than some t, right? And so now because you have these weights, all of a sudden, you can basically learn by some process, and as a result, the weights are going to change through some training process, right? So actually, we're going to write this in a little bit of a different way, right? So how we're going to rewrite this, we're going to say y is some sigma of xi wi plus b greater than 0. Oh, sorry, not 0, just of b. All right, so you could draw this in this manner now. So I have my x's, x1 to xn, w1 to wn, and then you could almost say there's like a b here, and that there's a sigma here, and then that produces my y. Okay, so it should be clear that essentially what this b is doing here, right? So let me just, this b is basically taking the function of this if what we do is we set, sorry, where, oops, wrong color, where sigma of t is just indicate a function of t greater than 0, right? So now we're basically the sigma, the function, this is the sort of the thresholding function. This does not have a parameter anymore. We sort of push the parameter into this b, which is called the bias term. Before we had this t, that was the parameter. Now we just set it to be b, and our function is no longer, it's just greater than 0. Okay. So this is Rosenblatt's perceptron. Any questions so far?
What does B do?
Sorry?
It's over there. Why we have the B? What's it supposed to try and correct for? Maybe could you repeat that?
Oh yeah. So sure. So if we go back to this model, right? So I just claimed that it sort of makes sense that you should have some t here, right? Because the threshold is going to depend on basically the inputs, right? The only thing that's sort of changing in this model, the only thing that you can tweak is your t, right? So maybe you would want this thing to not actually fire that often, so you'd increase your t, right? So that's t, right? And then we said, okay, well, actually we can create weighted versions of them, right? So we create weighted versions of them, and then we could set this, then we have a different t, right? But here, all I'm doing is basically sort of recharacterizing this. Instead of having this be greater than some t, I'm just going to say, let's say this is greater than 0. Okay, let's not put t here because I guess it's a little bit confusing. Right, so what's a good sigma of a is greater than 0. And so I'm just saying, the actual function itself, I'm going to have it to have no parameters here. So sigma is just some deterministic function without any parameters. And then if I set b correctly, then that's going to be equivalent to some choice of greater than t, right? So in particular, we could rewrite this as equal to indicate a function of sum of xi wi plus b greater than 0. So if you wanted to recreate it, you would set b equal to minus t. So essentially what this b is sort of dictating the threshold you pick in this particular case.
Thank you.
Yeah. Okay. So yeah, so I think it's pretty intuitive so far, right? So like as I said, like this is motivated by biology. Obviously we take a lot of simplifications, but it sort of makes sense, right? Like I have some inputs, I take away to some of them. These are sort of like the information I'm taking in, and then I have some choice. Do I fire? Do I move on to the next step or not? And so that's what the output is, right? Okay, so that's Rosenblatt's perceptron, right? So some things that are pretty interesting about. Okay, so one other thing that yeah, this is somewhat important, right? So I'm going to call this the universality of perceptrons. Okay, so if you think about what we're trying to do, right? We're trying to, we have some input and we have some output. So it's now let's sort of forget about the biology from this. Really what we're trying to do is we're trying to model inputs and outputs, right? So the relationship between inputs and outputs, right? And so you might be interested in sort of seeing, how powerful are these representations that you can have if you have multiple perceptrons, okay? So one way you can think about this is thinking about this in terms of like a computer, okay, where you have bits of data, zeros and ones coming in, zeros and ones coming out, and depending on what happens in between, you can basically end up creating computers. Okay, so for instance, let's look at this particular perceptron. So I have x1, I have x2, right? They come in here, and my bias term is 3. The weights, I'm going to have a -2. Oops. Right, my sigma, that produces an output. Okay, so in particular, what I'm going to do is, because I'm thinking about this in terms of like binary data, so my x1s and x2s are actually going to be 0, 1, right? So let's look at what this perceptron actually does, right? So I have x1 and x2, and I have y, right? So it could be 1, 1, 0, 0, 1, 0, 1, 0, right? So these are the 4 possible inputs that this gate, so this is a logic gate, right? This logic gate can potentially take. Let's just do the math and calculate it, right? So, okay, so what is this function actually? This is basically y equals to indicate a function of 3 minus 2x1 minus 2x2 is greater than 0, right? Okay, so you can do the math, or you can just read it out. So let's see, blah, blah, blah. This is going to be 1, 1, so it's going to be in 0. Nope. Any of these is, so it'll be 3 minus 2, that'll be 1, 1 is greater than 0, that's 1, that's 1. If there's 0, 0, that'll be 3, greater than 0 is 1. Okay. So does everyone see what I just did there? So basically I have x1 and x2 are my inputs and y is my output, and the perceptron is basically this function. Okay. Importantly, if I am looking at zeros or ones as my input, then I can get back this table. This basically completely describes the function of this gate. Anyone know the name of this gate by any chance?
Is it an XOR?
No.
Isn't it a NAND gate?
Yes. Yes. So this is a NAND gate. Whoops. This is a NAND gate. And the reason why I bring up this NAND gate is because NAND gates actually have a very important property, which is that if you can represent a NAND gate, then you can essentially represent anything as a combination of NAND gates. So sorry, I don't mean like anything, but you can basically represent any computable program as a combination of NAND gates in different configurations. So NAND gates basically have this sort of universality property in terms of computation. Okay, so they're really important as a fundamental sort of unit of computation. This is more CSE stuff, so I don't want to get into too much of it. But the key point here is that there's some sort of nice property of perceptrons simply just because they can represent these NAND gates. You can basically construct almost any. You basically construct a whole computer with these perceptrons. Obviously, we don't. So part of the reason why we don't is because even though it's possible to do this, it's not at all very efficient, right? And so actually what you would get a very complicated, prohibitively complicated graph that involves NAND gates, like millions and billions of NAND gates put in some configuration. Okay, so I just wanted to bring this up just because a lot of times, I mean, we'll see this in this lecture, just because something is universal doesn't actually mean it's great in practice, right? So perceptrons in some sense are universal in that you could basically run a computer with them. But in practice, we're not going to do that because they're not that great. Okay, any questions? No questions. Yeah, so yeah, I mean, this part is fairly straightforward, I would hope. Okay, so let's, so far, this is sort of boring. We're just taking like a few inputs, taking one output. Now we're going to get into multi-layer perceptrons. Okay, so multi-layer perceptrons. What is this? This is basically when you have multiple perceptron units. Okay, so I'm not going to draw all of them. I guess I will. Right. Okay. So what we have our input X. We're going to call this H1. Actually, I'm going to draw another bunch. Just because I want to explain something in a little bit. Okay. Maybe okay. Whatever. Okay. So let's call this H2. Right. So what we just had was a simple perceptron that takes a bunch of input and gives me one output. Okay, but clearly I can do this sort of in a multi-step manner, like sort of concurrently, right? So what I'm going to write is I'm going to write this in the following way. So this is going to be W1, it's going to be W2. Okay, so then what I'm doing is I have my input X, right? So then I can basically write H1 equals to sigma of W1X plus B1, where this is the bias term, which I actually don't sort of, I don't put it in there, right? And sigma here, for now, just think of it as sort of the 0, 1 threshold. Okay. And then, well, we could have H2 equals to sigma of W2 H1 plus B2. Okay. So this is sort of sloppy. And if you've worked through the homework, you sort of will have recognized this. This is sort of sloppy behavior, sort of sloppy writing, because the key point here is that, what are we doing, right? This is basically putting all of these guys into, one diagram, right? So, in some sense, what we have is H1, this is sort of silly. So I guess the first index, H1 of 1, right? Okay, no, let's just put the 1 at the top. Yeah, that's fine. So the first index of H1 is sigma of W1. Okay, this is no. Okay, so I'm gonna put the numbers at the top, because actually it's gonna get confusing otherwise. Sorry. So this is H1, H2, H1, H2, H1, W2, W1, W1, W2. Okay. Ba-ba-bum. Right. So H1 here, H1 here is a vector, right? And we look at just the first element of that vector. Well, if you sort of look at the picture, that's just basically, this is just one of the perceptrons, right? I have all this input and it gives me the output, right? So that would be sigma. Well, then that would be W1, 1 times X plus B, right? And then this could be H1, 2 is sigma of W2, 1 plus B, right? So essentially, this is basically, this would be sort of the exact thing you're doing, but this is just the way we write it, right? So the key point is that these sigmas are are applied element wise, right? So this is not across the whole value itself. This is just basically an element wise, right? This is how you get from sort of these single perceptrons to multi-layer perceptrons. Does that make sense? So just keep that in mind. So sometimes it gets a little confusing, because you should think of these sigmas as sort of applying independently across the my vector, right? Because this guy here is going to be a vector, and then I just apply the sigma on each element of the vector. Okay. So here's something to keep in mind. Let's suppose, so okay, I guess this is sort of, it's a little bit weird. So suppose actually I say, so right now, we've been talking about the sigma being, this sigma function being, particular one where it's like 0, 1. Suppose my sigma function is just the identity, right? Let's look at what happens if that's the case. Well, then what we'll have is we'll have H2 is, well, that's just W2 H1 plus B, right? But then that's just W2 of W1 X plus B plus B. Oh, I forgot the B's. There should be a B1 and a B2. This is B2, this is B2, this is B1. Okay, then that's going to be W2, W1 X plus W2 B1 plus B2. Okay, right. So what's important to realize is that if you just have the identity function, right? What you get is that, well, this is basically doing sort of, linear transforms. And the key point is that this is just then going to be, some W alpha X plus some B alpha, right? So if you don't have the nonlinear transforms, then having multiple of these, layers, because all you're doing is a linear transform and then you hit it with a nonlinear. So, okay, remember the threshold here is nonlinear, right? So what is this threshold thing? We're going to look at this a little bit later, right? But this is the threshold thing basically looks like that, and that's nonlinear. If you get rid of this nonlinear component, then everything is linear. And so if you basically append multiple layers, concatenate multiple layers, you're just going to sort of do something redundant. Okay. Although it turns out that even though this is basically redundant, right? Because what we're saying is this function here, right? If my sigmas are the identity function, then the thing that I'm learning is basically going to be a linear representation. It's going to be a linear function of my inputs. So I didn't actually need these, these intermediate W1, W2, because it basically boils down to some W plus some B, right? It turns out that there's the subtlety here, which is sort of the current state of the art research, which we've been looking at is sort of so this looks like it is a silly thing to do, right? Having linear activations. Sorry, this is linear. Basically, identity, right? So to have the identity for your functions here, so that your final thing you're learning basically collapses to a single thing, right? So this would be equivalent to a one layer, right? If you just had one layer, that would be you have your W and your B, right? But it turns out that for certain types of problems, this is actually useful. Like having these multiple layers is actually useful simply because you've over-parameterized the problem. And for some reason, by over-parameterizing the problem and allowing yourself to run stochastic gradient descent, you can get better results, even though in some sense, these things are equivalent, right? So, okay, I know this is getting a little bit technical. If I have time, I'll talk about this later on. But it's actually really interesting that, what I'm saying here is that it seems like these things it would be silly to have a linear activation function. Okay. If you didn't understand that, don't worry. Revisit it once we go through the rest of neural networks. Sorry. Yeah, if you're interested in that, come talk to me later. Okay, so so really, you had perceptrons. Now we're sort of aggregating them up, and we're sort of putting them, next to each other. So now you can get something more and more complicated. And they actually end up being pretty powerful, right? So it turns out there's this theorem called the universal approximation theorem, UAT usually, right? So before I describe what the theorem is, I just let's take a step back, right? So what are we doing? We have our inputs X, and we have some output Y, right? And this is what we've been doing throughout this whole class, right? We want to basically model that function. Suppose there is some function y equals f of x. We want to basically model f, right? So we're trying to basically figure out an f hat that well approximates the true y equals f x. Okay, so what does the universal approximation theorem says? It says that essentially a feed forward neural network, sort of with one hidden layer, right? So basically a neural network with just one hidden layer, whoops. with nonlinear activation, sigma can approximate any Borel measurable function from Rm to Rn, has to be finite dimensional, to any degree of error. Okay, so there are a few things in this statement that I need to explain. Oops, someone has a question. Just to confirm, the W's linearly combined for each X and are not element-wise combinations. What does that mean? So what I'm saying here is that, you know, so for instance, you could, let me see if I draw somewhere else. Okay, so
Professor, can I just just wanted to quickly explain the question. I just wanted to clarify that when you multiply the x's by the w's, it's not that w1 only multiplies x1. Like you could actually have w1, w2, w3 all combined, like it's like a linear matrix.
Yes, it's like a sum here.
A dot. Okay. Okay.
Yeah. So it's like so I'm this multi-layer is a generalization of this, right? Because essentially what I'm saying is let's do this multiple times, and so for one output I'll need a set of w1 to wn's. For another output I'll need another set, and I just concatenate them into a matrix. That's my that's my full W.
Cool. Thank you.
Yeah. Sorry. Okay. Yeah. Okay, so let's try and understand what this is. First of all, what is feed forward? Feed forward basically means that these things, the arrows here are basically going forward, right? So you never have an arrow that goes backwards, right? So it'll be weird to have an arrow that goes backwards, but basically you don't want loops, right? So these things are just going forward. I have my input, they go forward to some hidden layer, they go forward eventually to the output. Okay, so that's what a feed forward neural network is. So we have one hidden layer, blah, 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 that's fine. It can approximate any Borel measurable function. If you've taken measure theory, you'll know what that means. Otherwise, basically think of it as like, something that's continuous, like a nice function. Like it can't be like too crazy. Otherwise, it's impossible to approximate it. So essentially what this is saying is that all you need is a one layer neural network, right? And it's if with that one layer neural network, you're essentially able to approximate any smooth continuous function to any degree of error, right? And this is finite dimensional, so M and N can be humongous, right? So this is a really okay. So if you don't, it sounds like a really, really big deal. Well, it is somewhat like a really big deal. And yet, right? And yet this is not the state of the art, right? Because this is just one hidden layer. So can anyone tell me why this is not as amazing as maybe it first sounds? What's the issue here? Oh, yeah. So we've not said anything about how many things per layer, right? Good, right? So one point here is that, so this is basically sort of the width of the neural network. So depth is sort of, we talk about the number of layers, that's the depth. Width is sort of how many hidden units there are, right? So in this case, we have 3 hidden units. Our H is in R3. Yeah, so actually it turns out that for this, we would need exponentially many hidden units. Okay, so let me just write this down. So the first problem is the notion of width, right? So this proof actually requires can't spell exponential number of hidden units. And actually, there is a paper by Barron, 1993. And Barron is of 242 infamy, where he provides bounds on the size of these neural networks to approximate classes of functions. Okay, so if you guys are interested, you can read. There's a paper by Barron, 1993, that goes into sort of the proof of this. Okay, so that's one thing, right? So you actually need a lot of hidden units. So another possible answer is what if our data does not follow a clear function? If there are little oddities in our data, might we want more layers to be able to model those? Okay, so yeah, so this is getting at, I guess, the question of this requirement that it has to be somewhat continuous. And I think, so in general, if your thing is not if your thing is not very well behaved, right? It doesn't matter if you have well, actually, so this may or may not be true, but intuitively, I think this is true. If your thing is not that well behaved, then having high, large width or large depth is not really going to help you, right? You sort of need these things to be well behaved because ultimately, you expect these things to be pretty predictable. So maybe it's true that depth is better able to capture cases where the function you're trying to learn is a little bit is much more jaggedy. I don't think we have theory on that. So that's not part of the answer. I mean, maybe it is part of the answer, but we don't know if that's true. What else? So this here is, might not be able to find a good approximation in the parameter space. So in this parameter space, so I'm claiming that this, like the parameter space of just feed-forward neural networks, right? So this is the whole space. I am claiming that you can find one that approximates it to approximate any function to any degree of accuracy. So that's not actually it. Then okay, someone says computation time. That is part of it. So okay, essentially, sort of what you guys are saying is essentially right. Yeah, essentially the key point here is that this is an existence proof, right? So this is saying that there exists a feed-forward neural network such that you can basically approximate any function. There's a huge difference between something existing and being able to actually get it, right? And one of the things about, well, maybe you don't know, one of the key points about nonlinear optimization, right? So here, because we have a nonlinear activation function, it's going to be nonlinear, right? So all of a sudden, that just means things are ugly. It's no longer convex. And so as a result, for one thing, there's, you cannot actually access this because what we're doing all the time is running stochastic gradient descent, right? So that's just some greedy type of algorithm that's basically, moving in the direction of the gradient. That's not going to get me necessarily to the optimum solution. Okay. So essentially it's a combination of these 2 points. For one thing, the actual solution is going to be incredibly large in terms of its width, right? And then the second thing is that, well, this is just an existence proof. How do you actually find that proof? How do you actually find this particular neural network that actually gets you what you want is actually much harder. And we don't have any guarantees that stochastic gradient descent actually can find you that particular thing you want. Does that make sense? Right. So I'm saying, like, I'm thinking about all possible neural networks that are one layer deep, right? And as a result, I have all these parameters, right? So what are the parameters here? The parameters corresponds to the W's and the B's, right? Right. So these are the parameters, right? My W's and my B's. And so there, so if you have enough width, right? So if you have enough hidden units, there exists a configuration of my W's and B's such that for any particular, for any particular function, there exists a configuration of W's and B's that would do really, really well in approximating this function. The reality is we kind of, it's hard to find that configuration for each function because this is nonlinear. Okay. So what we're instead going to do is we're just going to say, let's just forget about this universal approximation theorem, right? And instead just try increasing depth. Okay, well, actually, I guess I should write that. Okay, let me just, I'm just going to write this in terms of existence versus computation. Right, and we always use SGD. So that's part of the issue there. So what we're going to do is we're just going to go deep. Right. So we're essentially going to forget about this universal approximation theorem. Actually, people are trying to create a universal approximation theorem in the same spirit, but for deep networks. Andrew Barron again is working on that. I don't think they've found something nice to sort of close the book on this chapter. So there's not much theory here, unfortunately. But let's try to give you some intuition as to why maybe depth is better than going wide. Actually, if anyone has any intuition or some inkling as to why they think going deep is better than going wide, please write it in the comments while I write some stuff, or you can mention it. Deep can utilize the coefficients more efficiently. Would you care to explain what you mean by that? Some weights can be shared by the next layer, I guess. Some weights can be shared by the next layer. So you're sharing the next layer. So you're actually like keeping the weights or something? Okay, well, yeah. So first of all, this is just all intuition. So another suggestion, could depth also easily mimic the exponentiation required of width? Yeah, okay. And then someone says deep somehow breaks the problem down to subproblems, which can be solved in parallel or easier than one massive layer. Okay, yeah, so these are all good suggestions. I mean, I'm basically gonna write out what you're basically going to say. So for me, at least, the way I like to think about this, so there are two ways to think about this, right? So if we go back to the NAND gate intuition that we had there, you think about it as like a computer program. It takes some input and it creates an output, right? And if you think about the way we write computer programs, is there are subroutines, there are intermediate variables. You're basically doing something step by step, right? And so actually, you can think of the layers of a network as a computer program. So you think of a neural network as a computer program, and so as a result, depth basically takes the role of being able to do processing. You could say it's in parallel, or you could say like, yeah, I'm creating intermediate values, I'm storing things, I'm using things from before, and that process gives me a lot more flexibility than the alternative, which is like, okay, I take one step, like I start with my input, I do everything in one go, and then I'm done, right? So intuitively, it sort of makes sense that width is a little bit more brute force than the nice thing about if you have depth, where so you can sort of interplay variables between each other and let things sort of progress. Okay, so so I guess one way you can think of it is sort of like a computer program. Okay, and so actually one other intuition is so this relates more to image processing, which we're not going to cover. I actually don't know where at Yale they talk about this, but so essentially convolutional neural networks are for image processing. It's a type of neural network, and one of the things you notice when you actually run these is that they mimic the way our eyes process visual data. And intuitively, the way you can think about this is that you have your pixel information, and then what's going to happen is that these first layers are going to pick up on like low level features, so like edges, gradients, so like changes of color. So you have things like edge detectors and whatever. So these are called Gabor filters. If you're interested, you could read more about convolutional neural networks. But these are sort of like the fundamental building blocks of analyzing images. So like you start with sort of these low level features of an image, and then eventually you sort of start building mid-level features. Let's say a patch of some circle, for instance, or triangles or whatever, and eventually you get to your high level features, which is like sort of the last layers, which correspond to actual high level. So maybe say a hand, right, or a dog. But I guess a dog would be way too high level. But yeah, so you sort of get the picture. Here, what you're doing is you're in some sense as well, you're breaking down your problem into smaller individual problems, and then you sort of concatenate. You sort of like accumulate information as you go forward. So it sort of mimics sort of visual processing in the brain. Okay, so yeah, so one other intuition comes from sort of the visual processing from a brain, and it's a bit like incremental learning. You're sort of like learning more and more complicated features of your data as combinations of the lower level features. Okay, so I think these are pretty like convincing arguments as to why we would look at depth. The sort of the annoying thing about all this is that, in fact, there's just very little theory to guide our intuition. I mean, obviously we're all working on this, and we're trying to, come up with a lot of principles. But reality is that this is a lot of it is just somewhat ad hoc and engineering based. Okay, so so now we're sort of basically at the I would call it it's like the recent era of neural networks. So we're at the recent success of neural networks. right? So the key point was that what you have is you have deep networks, right? And actually, one of the most important things that people don't really think about, but I guess it's pretty clear when we teach this class, is that you really need data, right? You need a huge amount of data. Oh, did someone say something? Or okay, so you have data, and then you basically need compute power, because what you're going to do is you're going to basically have increased depth, right? So let's say 100 plus layers. You're going to have sort of fancy architecture that's going to be like, domain specific. We've looked at recurrent neural networks. I briefly maybe mentioned LSTMs, convolutional neural network. These are all different types of architectures. Although they're basically all neural networks. So you just play around with how these things look, right? And this is basically engineering, right? You're sort of just playing around with stuff and seeing what works. And then ultimately you care about like doing this for as long as possible. So there are a lot of computational tricks, regularization tricks, and so on and so forth. Okay, all of that adds together to basically give you this recent, amazing reality of these neural networks sort of beating everything else under the sun for most tasks, essentially, right? So as a brief example of the timeline for these things, so this is in 2012. There was like there is a data set classification problem, image classification problem called ImageNet. Sort of in 2012, AlexNet was sort of the state of the art, and this had basically 8 layers, right? Then by 2014, you had basically Google.net, which was 22 layers. And that by that point, that was a roughly 4 million parameters, right? Some crazy examples here, VGGNet, which was also 2014, that had only 16 layers, but then it had 138 million parameters, right? So, I mean, like the sheer scale of these neural networks, I think is sort of, I don't know, it's just out of this world. Like 138 million parameters you need to tune. And so obviously this is now, in the realms of yes, because like this is all about computational tricks. How do I, store these things in memory? How do I feed in the data? What are the ways I can do to make this actually, run in some reasonable amount of time? Right. So like, I think the sort of the history of it was a little bit more like, theoretical statistics / machine learning. It was much more theory based. And then this recent explosion in sort of performance, a lot of it is now sort of, the people at the front of this are just the CS people, because most of this is now sort of, how do you make this actually work in practical time? So in, what was this, 2015, you had these people in Microsoft who won ImageNet, and this was like 100 layers and like, infinitely many parameters or something. Just some ridiculous number of parameters. Okay, so, but ultimately, all it is a neural network, right? It's this multi-layer perceptron, except you're a little bit clever about your activation functions, and you're a little bit clever about the way you're going to set this up. But sort of deep, deep down, it really just boils down to this. I have these non-linear activations. I have these linear, I'm taking linear functions of the previous layer, and I just basically stack them. And for some reason, just this very simple process, you're able to get state-of-the-art performance. Okay. Any questions so far? Cool. Okay. So there are a few things I haven't talked about. Let's talk about activation functions first. Right. So I sort of glossed over this. If we look back to these perceptrons, the perceptrons are essentially this threshold function. So let's just start with sort of what happened before. I'm going to call this perceptron / threshold. Right. And what's that? That's essentially this, where I have this is a 1, and the function looks like this. Okay, or yeah, indicator of x greater than 0. Okay, so this is not particularly great for many reasons. Well, not many reasons. One thing which seems like it's not a great thing, but it's actually not too bad, is that this guy, at x is 0 is non-differentiable. Okay, and you might be asking, well, okay, well, first of all, why do I care if they're non-differentiable or not? So remember, what are we doing, right? So we're devising a model, right? This is a neural network, and it's going to be, blah, blah, blah. It has some functions, it has some parameters. And how do we learn these parameters? Well, we're just going to use stochastic gradient descent. What does that mean? We have to calculate gradients, right? Remember how stochastic gradient descent works? We have our parameters, and we're going to move our parameters in the direction of the gradient of the loss, right? So we need to calculate the gradient of the loss with respect to the parameters. And so clearly, we want to investigate what the gradients of these functions look like, because they're going to participate in the loss function and the gradient of the loss function, right? So one thing you might be like, okay, well, this is not that great because at x equals 0, this function is non-differentiable. Turns out it doesn't really matter because just, this is basically at 0. You can define a sub gradient, and so it's really not that big of a deal. What is problematic here is the fact that the gradient here is basically 0 almost everywhere, right? So gradient basically equal to 0. Okay. So I'm just going to leave that there for now, and then we'll come back to this. So just for now, let's just recall that. Let's just remember that the gradient equals to 0. Okay. Then what we've looked at, I think, before is basically this function called the sigmoid function, right? Oops. That's e of x over 1 plus e of x. That's going to be in 0, 1, right? And so then what's that? That is this. It's going to look like this, right? It's 1. Okay, so there are a few issues here. One thing, this is non-zero mean, right? And in particular, basically these functions, they saturate at the extremes. In particular, what that means is that, the gradients go to 0 as x goes to infinity, right? So again, I will talk about why I don't want gradients to go to 0 in a little bit, but just keep this in mind, right? So here I have, non-zero mean. Basically, that's just saying, okay, well, this thing is, take the average of it, it's going to be at like 0.5, right? So maybe you don't want this to be at 0.5. So what people then do is, okay, let's just reshape this, right? So that's actually how you get the hyperbolic tangent, which is what we've seen before, right? You can actually rewrite this as 2x minus 1 where the sigma here is just this guy, right? What that gives you is this function, where this is going to be 1, it's going to be -1, right? Okay, so now this is a little bit nicer because this has 0 mean, but it still saturates. Okay, so what am I doing here? So here I'm just looking at the different, essentially what I want is I want something to be nonlinear, right? If you remember, if I have it be linear, basically I can then rewrite everything in terms of just a one-layer linear unit, one-layer linear neural network. So it's actually not that nice. So I want some nonlinearities. The question is, what choice of nonlinearities do we have? You know, when you look at the case of you know, sort of the classical thing we talked about earlier in sort of history, they started off looking at these perceptron, which is just a threshold. It turns out that this is not very nice because this basically gives you 0 gradients of 0 throughout, right? So then people were like, okay, let's come up with like a smoother version of this. So sigmoid is basically like a smoother version of this, right? So it's, you know, it's a little bit like the threshold, but now I have a smoothed out version. As a result, technically my gradients are all going to be, you know, non-zero, but in particular, you know, as your x's get really, really big, the gradients are almost 0. Okay, sigmoid and hyperbolic tangent are basically sort of the same thing, except now I've sort of centered the sigmoid, which sometimes helps. But the key point is that ultimately these gradients are very in most of the domain that you define your functions, they're basically very close to 0. Okay, so so why is it bad for gradients to be close to 0? I feel like some people should know this since they've taken.
It'd be hard to change your gradient descent algorithm because your shift would be essentially nothing. So you just wouldn't be changing your parameters at all, or very, very slowly.
Yes, exactly. Yeah, that's exactly it, right? The gradients basically, because we're doing stochastic gradient descent, the gradients tell you where to go. But if your gradients are almost 0, you're basically, you know, you're not moving very far, right? You're basically not moving at all at some point. So I mean, this is why this one is really, really bad. Oops, sorry. This is why this one is really, really bad because my gradients are exactly 0, right? So I'm just, yeah, basically. So this is, yeah, also known as vanishing gradient problem. Okay, so what people came up with was, all right, let's just do something crazy, right? So what we do is we basically define something called the ReLU, which is max of x and I keep writing x and 0. What's that? That's this and this. Okay, so that's the ReLU function. So what are the nice things about this? This is still easy to optimize, right? Because, well, what's the gradient? It's going to be this, and then it's going to be 1, right? So this would be 1, that would be the gradient. And the nice thing now is that here, gradient don't vanish in the positive domain, right? Because the gradient is 1 there, so it actually does something. But it still vanishes in the negative domain, right? Although, you know, that might be something you want, right? Like you might want it to just give you 0. So, you know, in those certain situations, you don't really move. But people were like, okay, actually, let's, instead of making it exactly 0, why don't we just make it a small number, right? So what they came up with was just a really simple fix for the fact that the gradients are 0 in the negative domain. So what they did is, why should I do this? Yeah, okay, I'm just gonna call this here. They set up something called the leaky ReLU, which is max of x of 0 plus 0.01 of min of 0 and x. Okay, I mean, the function is not particularly important. The key point here is that what you have is now you have this, you have like a very, very small slope here, right? What that means is now, I have just small gradient there and a gradient here. This would be 1, this would be 0.01, right? So at least you can, back, I'm going to use the word backprop, even though I haven't described it. You can backprop, information can flow backwards so that you can actually, move, your gradients can still move. Okay, so obviously we will be talking about this, like this notion of like, backprop, what does that mean? But intuitively, because we're using stochastic gradient descent, we want our gradients to actually do something. So this is what we would prefer to use. Okay, so obviously it's not the case that actually every single activation function is a ReLU. If you look through my LSTM slides, you'll see that actually, like even with the neural language model, right? So a lot of times we use the hyperbolic tangent. Sometimes the reason why we use hyperbolic tangents in papers is because that's just what we used to use before people invented this. But other times, there's actually a reason why you might want to use a hyperbolic tangent. It just depends on sort of the function of the hidden layer, right? In this particular case for LSTMs, the hyperbolic tangent is useful as a way to access sort of the memory, the hidden memory unit. Yeah. Okay. Okay, so that's essentially what these activation functions are, right? So, okay, so if we take a little step back, what I'm saying, we have these neural networks that look like this, and in terms of like the most simplest architecture, you're just basically building multiple layers on top of each other, and you have a choice of activation function. Most of the time, you're going to pick the ReLU, right? Just because it's nice and easy, and that's what we use in the homework. Let's sort of, okay, I have 3 minutes, so I just want to take 1 second to make this particular comment, right? So what do we have, right? So we have our x's and blah, 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 blah. Let's call this P, right? So in the homework, what we looked at was I had this softmax of F, and then I'm going to define F to be, some Wx plus B, right? So here I've used softmax, right? And I haven't written sigmoid, right? So who can tell me what's the difference between softmax and sigmoid, right? Because it looks like they're almost the same thing, right? What I could have is, okay, I could have something that looks like this. I have my x's, blah, 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 blah. And then I have, let's say, h. And my h could be defined by sigma of wx plus b, right? And then the sigma here would be sigma a equals to e to the power minus a. Oh, well, don't remember. Sorry. E to the power a. Yeah. Over 1 plus e to the power a. Okay. So, I mean, yeah. So, okay. So what is the difference between these two? And intuitively, what's going on? They look very similar for one thing.
Wouldn't softmax ensure that you have a probability because it's over the sum?
Yes. Okay. Yes, exactly. What else can you say? So yeah. So when would you use softmax and when would you use sigmoid?
Well, you could use sigmoid like in the general application we were talking about just now, like in a perceptron neural net, and you can use softmax if you're trying to find the probability of, like in the example in the homework, of something being in one of several classes.
Yes. Yeah. So exactly. Yeah. So softmax, even though they're basically like the same thing, right? With softmax, the key point is that this is basically the binary version, right? And because we're doing it element-wise, it's not, it seems like it should be very similar because I have multiple inputs, I have multiple outputs as well, but the sigmoid, I'm going to write sigmoid here in case I keep forgetting. So this is the sigmoid, right? This is an element-wise operation. And so actually each of them are independent, right? Whereas with the softmax, and I mentioned this in passing when we looked at word embeddings, right? When I calculate this p, it's a function of everything, right? Because as you just said, the p is actually going to be a ratio, right, across everything such that they all sum up to 1. So that's where you get a probability distribution. And so as a result, this p, they're not like independent, right? With the sigmoid layer, you basically have independence because it's just going to be, well, it's not independent, but the value of one of these units, no, the value of one of these units is just calculated through the W's and the B's, and that's not going to the W's and B's does not depend on the other W's and B's, right? Whereas in this case, everything is dependent on, in order to calculate this one value, I need to calculate this value and this value and this value. So you have a much more computationally annoying dependency graph here. But the reason why we do this is because we want this to sum up to 1, right? And so you have to do this. Whereas with the sigmoid, you are basically taking this element-wise, and so as a result, you're still sort of treating them as like a hidden unit, and they're sort of independent in some sense. Okay, so that's that I think some people get confused by those two things because it looks like it's basically the same thing, but it actually really is very different. And softmax is essentially what we always use when we do classification at the end. And sigmoid is something that happens in the intermediate step where you have hidden units. Oftentimes when we talk about softmax, even I won't even call that a nonlinear, even though obviously it is nonlinear. But if you think about when we do logistic regression, we're doing a linear transform at the nonlinear transform at the end, but we still treat it as like a linear model, so to speak, right? So sometimes I will treat the softmax as not the linear part, as I just sort of forget about it and I consider the nonlinear actual hidden layers. Okay, so next lecture we will be talking about backprop, and I guess we'll have some concluding remarks, I guess, and maybe if I have time, talk more research. Okay, cool. Any questions?
I have a couple of course-related questions.
Sure.
So the first question is, what's the state of the mini quizzes these days? Because we wrote the one, and then I don't know if unless I missed it, I don't think there's been any further mini quizzes.
Yeah, I was meant to write one, but then I guess people don't particularly want another one. So, unless unless there's people who really want, I guess we don't need another one.
How does that affect the grading scheme then? Like, will the one mini quiz be weighted like 3, or will it be weighted less? Like, what's kind of going to happen with that, I suppose?
Yeah. Wait. So do grad students still have
Yeah, we still get a grade, so
okay.
It kind of matters.
I guess personally, I wouldn't worry if I were you. But in more generally, I guess I could give grad students a mini quiz.
I'm not saying I want to write a mini quiz. I'm just kind of, I guess just wondering what the grade distribution will be now.
Yeah. Okay. Also, I just feel like, you know,
I honestly,
just,
I prefer to weigh the earlier stuff more if I had to make a choice, but
yeah, no, I